The Enigma machine helped encrypt Nazi secrets, and the bombe was the machine built to crack it. Both machines changed the course of history, and both are, at their core, simple finite state machines. In this video, I'll show you how to build an Enigma from an EPROM. In the next, we'll use this EPROM-based Enigma to build a basic bombe, then we'll look at the enhanced bombe with the Welshman diagonal board. I'm Matt Regan. I have a PhD in computer science, and I previously worked as a GPU architect at NVIDIA. Just to restate, the aims of this series are 1. To look at finite state machines in more detail, to look at the design of the Enigma and the addition of the Plugboard, to understand how the bombe cracked the World War II Enigma, next, to understand how the Welshman diagonal board worked, and finally, to examine the relationship between these machines and a Turing machine. So, by the end of this series, you should be able to understand exactly how these early computing machines worked, and maybe even peer into the mind of Alan Turing. The Imitation Game is one of my favourite movies from the 2010s.
This war, we're not winning it. If you speak a word of what I'm about to show you, you will be executed for high treason. Who are you?
Alan Turing, one of the best mathematicians in the world.
Welcome to Enigma.
It's the greatest encryption device in history. The Germans use it for all major communications. 159 million possible settings.
It's unbreakable.
Let me try, and we'll know for sure.
It brilliantly shows how Alan Turing and his team at Bletchley Park did the unthinkable. They broke Enigma. The story actually starts in pre-war Poland with the incredible work of mathematicians like Marian Rejewski, but today I want to focus on the Enigma with the Plugboard added, which was used by the German Army and Air Force during World War II. When I watched the film, I'm struck by how this seemingly insurmountable problem boiled down to something surprisingly simple, a finite state machine. But they didn't really explore exactly how this machine worked. I know this wouldn't be popular in a movie, but it's the sort of detail I want to know.
The latest intercept.
The Army and Air Force Enigma was the cornerstone of German military communications during World War II. It was an advanced cipher device that used a series of rotating wheels, or rotors, and a plugboard, which could scramble messages into seemingly random gibberish. With the same settings, it could turn this gibberish back into the original message. The Germans believed that even if the Allies captured an Enigma machine, the sheer complexity of its settings would make deciphering messages impossible without knowing the exact rotor configuration, plugboard connections, and starting positions. Combinations that changed daily. But what the Germans didn't anticipate was the power of mathematical insight, algorithmic thinking, and indeed their own confirmation bias. Enter Alan Turing, Gordon Welshman, and the team at Bletchley Park, who realised that a brute force attack wouldn't work, but an algorithmic approach might. They designed the bombe not to try every possible setting blindly, but to methodically eliminate impossibilities, narrowing down the search space with incredible efficiency.
Well, what if Christopher doesn't have to search through all of the settings? What if he only has to search through ones that produce words we already know will be in the message?
Look, like this one. 0600 hours, weather today is clear, rain in the evening, Heil Hitler.
I'm going to make the assumption that you're relatively familiar with the inner workings of the Enigma. If not, I'd really recommend this video by Jared Owens, links provided below. The Enigma was an electromechanical cipher device that encrypted messages using a system of rotating rotors, a plugboard, and a reflector board. When an operator pressed a key, an electrical circuit passed through the plugboard, where a pair of letters could be swapped. Then, through a series of 3 rotors, each with 26 internal wires that randomly scrambled the signal. After passing all 3 rotors, the signal hit the reflector, which sent it back through the rotors via a different path, further scrambling the output. Finally, it went back through the plugboard and onto the lamp board to illuminate a letter. Each key press caused at least one rotor to rotate, changing the wiring alignment and creating a new encryption pattern for every letter typed. Even if we type the same letter over and over again, it'll be encrypted as a different letter with each keystroke. This constant shifting of electrical pathways, combined with the daily changes to the rotor settings, plugboard pairings, and rotor ordering produced a cipher that the Germans believed was mathematically unbreakable. Even if you don't completely follow this next section, the main take-home point is that the plugboard provided most of the complexity, and from an algorithmic perspective, this is where Turing and his team really attacked it beyond the work done in pre-World War II Poland. The standard Army and Air Force Enigma had 5 rotors, and we had to choose 3 amongst the 5. We have 5 choices for the first rotor, 4 for the second, and 3 for the third, giving us 5 times 4 times 3, or 60 combinations in all. On top of that, we have a starting letter for each rotor, so that's 26 times 26 times 26 possibilities. This comes out to about 1 million possible settings in total. Now, technically there are 2 settings per rotor. The ring setting, which would rotate the interior wires relative to the casing, and then there's the actual starting position of the rotor itself. Ignoring the notch on the rotor for the moment, the initial setting advances the wire in the rotor forward, and the ring setting moves the internal wiring in the rotor back in the opposite direction. If there are 2 possible settings per rotor, and there are 3 rotors, why aren't there 26 by 26 by 26 by 26 by 26 by 26 possible combinations? Well, from a wiring perspective, there's a simple relationship between the initial setting and the ring setting. Let's look at this example where the ring setting's AAF and the initial position's AAG. John Lennon's famous lyric gets encoded to AKGFL, RYLPO, so forth. When we reset the machine to the previous settings and type in the encrypted message, we get the imagined lyrics back. What we've done is advance the initial settings in the right rotor forward by G, which is 6 positions, then wind it back by F, which is 5 with the ring setting. Let's see if we can decode this original message with AAA and AAB. We see that the messages match for a while, then it's scrambled for a while, then it matches again. We know that one of the middle rotors rotated here, while with the alternate settings, the middle rotor rotates here and catches up. This is relatively easy to spot, and for decoding purposes, we can just assume that the ring setting's AAA and call AAB the adjusted initial position. Once we know the initial adjusted position, with a little bit of text, it's relatively trivial to figure out the actual initial position and ring setting. Because we're going to assume that the ring setting's AAA, what we're after is the adjusted initial position, which has 3 alphabetic characters, hence 26 by 26 by 26 possibilities. Putting this together, we have 5 by 4 by 3 by 26 by 26 by 26 settings, which is what we saw before. So this is the formula for calculating the rotor settings. The plugboard is really where the number of possible configurations explode. I'm going to use this Enigma emulator to demonstrate my point. In standard use, there are 10 wires, which swap 2 letters at a time, so 20 of the 26 letters would change at the plugboard and 6 would remain the same. A wire connecting BQ means that if B is pressed on the keyboard, then Q is sent to the rotors, and if B comes back from the rotors, then Q is displayed on the lamp board. We have 26 places for the first plug of the first wire, and 25 remaining places for the second plug of the first wire. Here I've connected BQ with a virtual red wire, but it doesn't really matter if we connect B to Q or Q to B. These are equivalent. So for the first wire, there are 26 by 25 divided by 2 possibilities. For the second wire, I have 24 places for the first plug and 23 for the second plug, but again, connecting C to R is the same as connecting R to C, so it's 24 times 23 divided by 2. We move to the third wire and we get 22 times 21 divided by 2, again because connecting D to I is the same as connecting I to D. We repeat this for the 4th, 5th, 6th, 7th, 8th, 9th and 10th wire, and we have this equation. The denominator can be simplified to 2 to the power of 10, and the numerator can be simplified to 26 factorial divided by 6 factorial. But we're not quite done yet. Although the wires are coloured in this emulator, on the real machine the wires are all the same, so the ordering of the wires doesn't matter. All of the configurations I'm showing here are equivalent. B is always connected to Q, C is always connected to R, and so forth. How many equivalent configurations are possible giving the same pairings? Well, there are 10 wires. we get to choose one of 10 wires for the first position, one of 9 for the second, one of 8 for the third, and so forth. So the number of combinations are 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 10 factorial equivalent settings. Because each set of pairings has 10 factorial equivalents, we need to divide the number of possibilities by 10 factorial. This gives us 26 factorial on the numerator and 6 factorial times 10 factorial times 2 to the power of 10 on the denominator. This comes to 150 million possible plugboard settings. This is a substitution cipher, and humans are quite good at cracking these. First of all, we can do frequency analysis. We know that E's occur a lot more frequently than X's. Second, double characters are a bit of a giveaway. For example, if we see SDDS, S is likely to be a consonant and D is likely to be a vowel, or S is likely to be a vowel and D is likely to be a consonant. There just aren't that many words that fit this pattern. There are lots of other examples like this, but the Germans thought that the moving rotors combined with the substitution cipher solved this. If we multiply this by 60 times 26 cubed, we get 159 million settings. The take-home message is that most of the combinations in this huge number come from the plugboard, not the rotors. The Enigma was an electromechanical machine, but I want to build one out of silicon. So the next thing I want to talk about is the idea of a finite state machine, which we can see here in the hierarchy of computing machines. The basic idea is to have some flip-flops which store state. Some of the outputs feed back to some combinatorial logic, which computes the next state, which feeds into the same flip-flops. On the positive edge of a clock, the next state becomes the current state. An easy way to build this combinatorial logic is to store it in a large EPROM. Now, the simplest example is an up counter. The flip-flops output an 8-bit number n. This feeds into the EPROM, which outputs the number n plus 1. If we output 0, the EPROM outputs 1. On the next positive edge of clock, this 1's latched into the flip-flops. The 1 feeds back into the EPROM, which outputs 2. And then on the next positive edge of clock, the 2's latched into the flip-flops. We can easily make an up counter from this, which I've demonstrated here. Notice the nice binary count pattern. In the case of the Enigma, the state held by the flip-flops is a binary representation of the current rotor setting. We have 26 characters per rotor, which we can encode with 5 bits each. 3 rotors at 5 bits each means that our state variable is going to be 15 bits. We program the EPROM in advance using the ring settings appropriate for any given rotor combination. A finite state machine can also have an input and an output. We'll make the input the key pressed, and the output is the lamp to illuminate. This is the state machine in action. We feed in the plain text at 1 character per clock cycle, then the associated encrypted character pops out on the positive edge of clock. You may need to watch this a couple of times to follow what's going on, but note that the state, representing the rotor settings, changes every clock cycle. We see the update occurring on the positive edge of clock, and the input character changes somewhere in the cycle. Here I've shown it changing on the negative edge of clock, but it can occur anywhere, provided we meet the EPROM propagation delay time and the setup and hold time for the flip-flops. Now, the actual Enigma uses 26 wires with a 1's hot protocol. This does change things a little when it comes to the Bombe, but we'll discuss that later. These EPROMs are quite large, 4 megabytes each, but the data encapsulated in the EPROM includes the ring setting, the rotor configurations, as well as all the plugboard settings. This little printed circuit board has an EPROMs with the outputs going into some flip-flops, and underneath, I wire it up to form a finite state machine. I have an Arduino Mega for controlling the initial rotor settings with these push-button switches. The upper button increases its associated rotor setting, while the bottom button reduces it. On the left, we have the initial rotor setting in SX, and this digit here is our first letter. I'm going to code the message Wettervorhersage Biscaya, pardons for my poor German, which means weather forecast for Biscay. Once I'm happy with W, I press the encode button and it comes out as an H. I repeat this for the entire message and my encrypted text looks like this. This encrypted text is sent out over radio waves using regular Morse code. At the receiving end, I should be able to feed the encrypted text back into an Enigma with the same initial rotor settings, and I should get the same answer out. Excellent. We've just encrypted and decrypted an Enigma message. But how do we generate the data that goes into the EPROM? First, we need to store data for the rotor settings, reflectors, and ring settings. Turns out all of this information is readily available on Wikipedia. We set aside some space for the plugboard pairs. Then we have a routine that hardwires in the plugboard settings. At first glance, this is a bit of a problem, because it basically means we need an EPROM pair for each of the 150 million plugboard settings. But we'll deal with that in a minute. In the main section, we clear the EPROM, program the plugboard, then we sweep through all initial settings from AAA to ZZZ. In the real Enigma, the act of pressing a key mechanically advances the rotor, so we have this advanced rotors routine. If the middle rotor's at its notch setting, then we basically advance all three. This replicates the double-stepping phenomena that the Enigma is known for. Otherwise, we check the right rotor. If it's at the ring setting, then we advance the middle and right rotors. If not, we just advance the right rotor alone. Next, we sweep through all possible key press inputs from A to Z. We set up the EPROM address based on the current rotor settings and the current input letter. After that, we program the next rotor position. But here's where all the action occurs. We run the signal through the plugboard to see if it's been swapped. This is just a simple search through the plugboard string. Then we execute this decode Enigma routine. Remember, after the plugboard, we do a forward pass through the right, middle, and left rotors. This is pretty straightforward. We just look up predefined rotor string, offset by the current input and the rotor settings. We correct for overflow. Note that I have an ASCII to binary conversion. I could avoid this, but it does make debugging easier. Remember, I'll do just about anything to make debugging easier. We do a forward pass through the rotors, then we hit the reflector. This is just a straight lookup table query. After that though, we have to go through the reverse pass for each rotor. This is a little more complex, because we have to find the letter of interest in the lookup table, but we can just do a simple character search. Again, we do the ASCII offsets and handle wraparounds. Once we've done all that, we just return the value, which goes back through the plugboard, and we shift the result in the appropriate field of the EPROM. Done. That's basically how we make an Enigma from an EPROM. Now you might be thinking, okay, even if we know the rotor ordering, we still need a new EPROM pair for each plugboard setting. But I'm really making an EPROM-based Enigma to go into a new Bombe machine. Well, here's the twist. What I'm actually interested in is how Alan Turing and his team cracked the Enigma. The algorithm they devised and used in the Bombe didn't need to search through all 150 million plugboard settings. Provided they accurately guessed some text in the message, such as Veta Vorsaga Biscaya, and they got a bit lucky. They only needed to guess one plugboard setting for a carefully chosen key character that we'll look at in more detail in the next video. This cut the search space down from 150 million to 26. In fact, the real Bombe machine effectively tested all 26 guesses in parallel. So, our Enigma finite state machine for the Bombe doesn't need to know the plugboard settings. In fact, it's the job of the algorithm in the Bombe to infer the plugboard settings. Here's an emulation of the machine I'm going to build. It found one solution at NSX. It inferred 7 of the 10 plugboard settings, GH, CR, BQ, OS, KW, MT, and EJ. It also found that Y and V have no plugs attached. Once this is known, with some decrypted text, it should be pretty simple to manually figure out the remaining plugboard settings. If you want to know exactly how the Bombe reduced this search space from 150 million down to 26, then stay tuned for the next episode.